So we have a charge QA, which is an alpha particle at the origin at x equals 0. And that charge is plus 2e. Okay, that's 3.2 times 10 to the minus 19 coulombs. And then we have another object here, a proton, at x equals 5 nanometers. That's charge QB, which is just the fundamental unit of charge here, 1.6, times 10 to the minus 9 coulombs. The proton is initially at rest, and it's going to move out to some distance here, x equals 25 nanometers. And we want to know what is the final velocity when it gets out there. That's for part A. Okay, so so this is a non-uniform field, right? So charge QB is moving within the field that's generated by charge QA. And so sum of forces equals ma. That's not going to work because the forces are not constant and the acceleration is not constant. So we can't use that approach. We have to use work energy. Okay, so the work energy theorem tells us that the sum of the works done by all the forces is equal to the change in kinetic energy. And we're going to assume that the electric force is the only relevant force in this problem. So that means the sum of the works done by all the forces is just the work done by the electric force. Now the work done by the electric force can be calculated 3 different ways. The first way is F delta S cosine theta. Stop me if you've heard this before, but that's not possible in this problem because it's a non-uniform field. And this equation only works when you got uniform fields. So I'm going to have to use minus the change in potential energy. Okay? So I'm going to replace this with minus Q delta V. So it's going to be QB, because QB, that's the charge that's moving, and it's moving through the potential that is generated by the charge QA. That's going to equal 1/2 mv squared minus 1/2 mv naught squared. And that term is 0 since v naught equals 0. Okay, so let's calculate the change of potential. Let's see, the final potential, which is going to be out at x equals 25 nanometers, is KQA over RF, right? Remember, this is the final potential due to charge QA. So we use 3.2 for charge QA, and then the final distance is 25 nanometers, so 25 times 10 to the minus 9. So that's 0.115 volts. And the initial potential is KQA over RI. Okay, so that's 3.2 times 10 to the minus 19 again. And our initial distance is just 5 nanometers. So that means our initial potential is going to be 5 times higher. That makes sense. It's going to move from a higher to a lower potential as it follows the electric field lines generated by charge QA. Alright, so let's see. I get so minus QB delta VA, that's 1/2 mv squared. So let me plug in my values. QB is positive 1.6 times 10 to the minus 19, and then delta V is V final minus V initial, so 115 minus 0.576. Okay, the change of potential is going to be negative, right? It's moving from higher to lower potential, and since the final potential is lower than the initial potential, right? Higher potential to lower potential. And since it's change of potential, it's moving to a lower potential, the change of potential energy is going to be negative. And that's going to knock out this negative sign and give us a positive change in kinetic energy. Now, the mass of a proton, that's what's moving. The mass of the proton, if you look it up, is 1.67 times 10 to the minus 27. So when I calculate V from all this, I get V is equal to 9,400 meters per second. Okay, there's our answer for part A. Now for part B, let's see, this proton is allowed to move freely to infinity. How much work does the electric force do? Well, the work done by the electric force is minus QB delta VA, but in this case, V initial is still 0.576 volts. right? But V final is now kqa over infinity, and so that's 0. And so the work done by the electric force is minus QB times VF minus VI. So that's positive 9.2 times 10 to the minus 20 joules. Okay, and it makes sense that the electric force is going to do positive work here because the electric force points to the right and the motion is to the right. So it should do positive work. Okay, so we're done.